I'm Takashi Otonari from the University of Tokyo. I'd like to talk about non-uniform sampling strategies for NAF on 360-degree images. The theme of our work is novel view synthesis using 360-degree images of equirectangular projection (EOP) format. The 360-degree images are taken in a scene, and based on them, 360-degree images from novel views in the scene are synthesized. Novel view synthesis has been actively studied using common perspective images. Novel view synthesis methods can be divided into two categories, explicit and implicit, depending on the 3D representation. Explicit methods are easy to learn and easy to achieve high accuracy, but the representation is discrete and requires more memory capacity to achieve high resolution. In contrast, the implicit method, which treats 3D space continuously by coordinate-based network, can acquire high resolution without memory limitations, but has traditionally been difficult to learn. Since then, research on novel view synthesis using perspective images has been conducted as an advance of NAF. However, the problem of applying NAF to 360-degree images in NeoP format was not addressed. Therefore, the goal of our work was to apply NAF to 360-degree images in NeoP format. To achieve this goal, we made three contributions. First, since there is no public dataset to evaluate novel view synthesis of 360-degree images, we created new indoor and outdoor synthesis datasets since 360. Second, we proposed two non-uniform ray sampling strategies for applying NAF to 360-degree images. Our experimental results showed that it is quantitatively and qualitatively superior to original NAF in terms of both learning speed and accuracy. Finally, we found that our proposed method enhances the quality of real-world scenes in 360-degree images. As a related work, here's a description of NAF, the subject of this study. First, A assigns each pixel array from the camera center and samples 3D points along the array. In B, the 3D position and 2D viewing directions of that 3D point is input to the neural network to obtain color and density. Then classical volume rendering techniques is used to accumulate those colors and densities along the rays into a 2D image. Since this process is naturally differentiable, we can use gradient descent to optimize this model by minimizing the error between each observed image and the corresponding rendered views. Due to the characteristics of a 360-degree image of EOP format, NAF general ray sampling strategy is ineffective. Here, I introduce two problems and proposed method. First, spatial distortion in the high latitude regions. To test this, we compute the area where a pixel of an EOP occupies the unit spherical surface as shown like this figure. In a 360-degree image, high latitude areas above and below the image occupy a much smaller 3D space compared to low latitude areas. Therefore, a sampling strategy is needed to take into consideration the spatial distortion of sample arrays for training NAF model on 360-degree images. To solve this problem, we proposed distortion-aware ray sampling. This strategy reduces sampling probability during training at the high latitude regions of the image by considering the area in 3D space of each pixel in the 360-degree image. Intuitively, the higher sampling probabilities are assigned to lower latitude regions as each ray has to cover the larger space in 3D. Second, provide viewing angle. 360-degree images basically contains large low-frequency texture regions such as sky and ground, ceiling and floor, and it is wasteful to keep spending the same amount of learning resources there as are spent on the high textured areas. To solve this problem of wasting learning due to the wide wing angle, we focused on reconstruction loss during training. NAF learns by the squared error between the ground truth color and the rendered color for each pixel, and the low-frequency texture region is considered to be easily learned and losses are easily lowered. Therefore, we proposed content-aware ray sampling which converts the loss of each pixel into a probability during training and adaptively reduces the sampling probability of pixels with small loss. To combine to non-uniform ray sampling strategy, the sampling probability of each pixel is multiplied and normalized. Next, we describe the new synthetic dataset Synth360. We created a new synthetic dataset and use this in our work for two reasons. There is no dataset for evaluating an overview synthesis of 360-degree images, and errors in camera parameters affect the accuracy of an overview synthesis. Replica dataset and SynCity were used as the indoor and outdoor 3D models, respectively, and projected onto Blender to generate multi-view 360-degree images. Next, we describe our experiments using the proposed methods. First are the quantitative results. The left side shows the results from the indoor dataset Replica, and the right side shows the results from the outdoor dataset SynCity. The PSNO values and graphs for each epoch are shown. Quantitative results show that the proposed method has a faster learning ramp-up than NAF and better final accuracy than NAF, both indoors and outdoors. We also made qualitative comparisons between the 5,000 iterations and the 100,000 iterations. The figures show from left to right the ground truth, the results of 5,000 iterations and 100,000 iterations of the original NAF, and 5,000 iterations and 100,000 iterations of the proposed method. The proposed method can learn details even at 5,000 iterations, and the image results show that the proposed method can successfully learn in areas where original NAF had difficulty learning and artifacts were generated. In addition, we visualized how the sampling probability of a pixel changes during training. The image used during training is shown on the left, and the sampling probability of each pixel is shown on the right, with the higher probability being wider. In the early stages of training, resampling with distortion is dominant, gradually increasing the sampling probability of detailed regions, and as learning progresses, we see that the sampling probabilities focused on pixels that are difficult to learn, such as object boundary regions. We also experimented with indoor and outdoor real-world scenes. We set up the task to retrieve a set of training images at 6 FPS from a 60 FPS video and restore the original video. Qualitatively, the proposed method was better at learning details such as buildings. Similarly, the effectiveness of the proposed method was qualitatively confirmed in an indoor, real-world scene. Finally, I summarized our work. The theme of our work was an overview synthesis of 360-degree images using NAF. Due to the characteristics of a 360-degree image of EOP format, there are spatial distortion in the high latitude regions and a 360-degree wide wing angle. NAF general ray sampling strategy is ineffective. To solve these problems, we propose two non-uniform sampling schemes for NAF to suit 360-degree images: distortion-aware ray sampling and content-aware ray sampling. Since there is no public dataset to evaluate novel view synthesis of 360-degree images, we created new indoor and outdoor synthetic datasets since 360. Our experimental results showed that it is quantitatively and qualitatively superior to original NAF in terms of both learning speed and accuracy. In addition, we found that our proposed method enhances the quality of real-world scenes in 360-degree images. This concludes my presentation. Thank you for your attention.